welcome back, physicists. In this video, we are finally getting back into it. We've been working on the planetary stuff for the last several days. We will be hanging them up either tomorrow or Monday. Riley and Nick, if you're watching this, anything that you send me would be awesome. I will get it printed and checked and all that good stuff. Yeah. All right. So today we get to start the new chapter, and for this, I don't want it to feel painfully slow for anybody, but I do want you to be aware that everything that we're going to do today is everything that we've done in pre-calc over the last several weeks. So I'm going to try not to go crazy fast in case somebody's never seen the trig stuff. You guys, please help with that. Cool. So in Chapter 8, which is what we are starting today, Chapter 8, we are going to be looking and using a bunch of trig because within here, we're going to be looking a bit closer at rotational motion. Now, there's an opportunity for a couple different hands-on building or experiment engineering sort of stuff. Two things that I think of that I care with rotational motion. The first, trebuchets, launchers. How do we launch stuff, not just with a spring, but by using like medieval siege tactics, which are pretty awesome. Alternatively, we're going to encounter an idea known as torque, which if you have a bridge that wants to turn, because obviously it's like stuck to the edge of a canyon, it wants to turn rotationally, right? That's how stuff wants to fall. Maybe, just maybe, this would be a great place for us to do our bridge engineering as well. But we will get there. As we start with rotational motion, our first section is going to be how on earth we actually describe it. So 8.1 is going to be describing, and I'm going to be less bold here in a second, describing rotational motion. And that feels redundant now that I'm writing it, but that's all right. Okay, couple things. Please keep me honest about the trig stuff. Not everybody's seen it recently or maybe to the level that we're going to discuss it. But jumping in, the very first thing that we have to hit is if we're going to talk about something rotating, so like whether it's me or the planet, doesn't matter, we have to be able to talk about how fast it moves. And there's two ways you can look at that. We saw this in pre-calc, but we didn't hit it super hard in there. We can look at what's known as its linear speed or velocity, which is if you were to suddenly have something on it and it stopped, how fast would it go flying away? It's like a slingshot and you're throwing it. That's the idea. Or how fast does it actually turn? Now, if I say how fast is the Earth rotating, it doesn't really make sense to give me a speed with meters per second because it depends on where you are on the planet. At the equator, we're running about 1,600 kilometers per hour, I think. Where we're at, we're probably closer to 800 kilometers per hour for our linear speed. Why on earth would they be different? That's our first question I want you to just discuss. It's weird that this hits just like fisheries yesterday. Why are we physically in Alaska moving so much slower than somebody might be moving in Manila right now on the planet? We're on the same planet that's spinning at the same speed. Why are they moving faster than us is the question. Talk it out, good ideas, bad ideas. I just want ideas. As we're looking at this, what shape is our planet?
It's not long, I forget.
That's right, it's an oblate spheroid. Now, for all intent and purpose, we're just going to say it's a sphere, right? Okay, random question unrelated. Have you guys ever seen an MRI? Not like the machine that does it, but the types of pictures that an MRI gives you. Can somebody explain to me what those pictures look like?
Slices of the brain.
They could be of your brain. Like if you could take a human, and we're not going to physically do this right now. If you could take a human, here they are, they're living the life, and you could take a crazy sharp blade and cut really, really thin, what we call cross sections, right across them. At each point, you would see a different structure, right? So for example, if you're looking at the head, you're going to see like halfway through, and we're just going to look at it because there's some uncomfortable pictures. Have you guys ever seen an MRI? Oh, do you guys know what the uncomfortable pictures with the eyeballs that I'm going to? Cool. So let's check it. What we're seeing on this picture is going through somebody's brain. We're starting at the top, and you can see that at any point that didn't do what I wanted it to. I wish I could pause it. You can see the eyes show up as we run through it. But anyway, if we were to take a cross-section or an MRI of our planet, what would the cross-section of a sphere look like? So we don't even have to think about it. This is a three-dimensional shape. We don't have to do crazy. Check it out. Can you tell perfectly, and if we're going to pretend you're further away, if you were really far away, could you tell this is a sphere for sure? What shape do you see, though? It's a circle. If I were to slice right through the middle, do you agree I would see a circle? If I were to slice right through up here, would I also see a circle? So any cross-section that I take is a circle, right? Now, as we look at this, if we're thinking about the Earth and why we're talking about these things, you don't have to draw this, but let's look. If I took a cross-section at the equator, it might be this big. If I took a cross-section where we're at, is it going to be smaller or bigger? Smaller. So maybe the cross-section for where we are is just like this, right? Now, if I imagine that here's the 50th degree of latitude and here's 0 degrees of latitude as we're looking at it, they're both spinning at the same rate. Yeah, they both turn a full circle in a full day. Which one has a larger radius? At the equator or up near the pole? So the radius, remember, its linear velocity is what? Or angular velocity. How do I want to word this? You guys remember v over r squared? Velocity over r squared. The radius gets bigger, and I'm goofed up on that. That formula's coming out weird. You agree that larger circle means faster movement? Cool, I'm fine with that. Now, going into this, it's nice to think about, and I think we actually get to calculate how fast our world actually turns here in a few minutes, which is pretty cool. But our first idea is we can't just talk about speed. So instead of speed and talking about just how much actual distance do you travel, we're going to cover a little more bold, angular displacement. Now, when we talk about how far has an angle changed, it's the same concept that we dealt with distance. We're just going to change units. We could talk in degrees. That would be reasonable. Is there another way to measure angles? Radians. So whether it's degrees or angles, if we're looking at how much the angle changes, what Greek letter do we use for this? Delta. It's a capital delta. And what's the go-to for an angle? Theta. Cool. Delta theta is all we're looking at. So real quickly, just as far as the definition goes, it's not a formal definition that I have here because I didn't do all caps, but I'm just going to say the change in angle. The change, and I'm going to be more specific, the change in central angle. Now, when we see the word central angle, I want you immediately to think of a circle, and you're making an angle at its center. Cool. Just like we do in pre-calc, but we're in here. Now, as we look at this, a full circle is how many degrees? 360 degrees. So we are not going to have to memorize this. If you are looking at this and you're rusty or you've been struggling and I'm unaware of it in pre-calc, I want to make sure that we at least hit this. If I have a lovely circle, and I should have just got it from Desmos, but that's okay. If I have I'm just going to get it from Desmos. Easy choice. So it took a minute, but I was able to perfectly draw a circle and even give myself nice graph just by jotting it down. Anyway, the question at hand was, what's a radian? Alex, I liked your answer, but I want a different answer. Not necessarily a different answer, but I want somebody else to hook it up. Mickey, Sean, or Huggins, what's a radian?
Like the amount of rotation in a circle.
So
Like the amount of
it can be. How many radians are in a full circle?
2 pi.
There we go. 2 pi radians in a full circle. That's fine. That's 2 pi r, right? Like it comes from the formula for the circumference of a circle. But what's 1 radian? 2 pi radians is a full circle. What about 1? Just 1. Okay. For this, if you don't recall, and I think some people do, what's this unit? What's that distance that I've just jotted down? Could be 1 if it's a unit circle, but on any circle we just call it this is a radius. I'm just going to call it r. It's a radius r. Now, it has a length, right? I could measure it. Is there a length, however long this is, that somewhere on this circle, if I started walking along, I would have the same length of a path? I bet it's pretty close to like right here. That's my guess. Now, I'm going to use a different letter than your book does. I use this arc right here. I label it S. pretty common to do this. We may see it in a physics class as a displacement, like a physical displacement, because you've been given some change in position and you can work out that distance. I'm going to call it S for now. When necessary and appropriate, I'll call it delta X to indicate, look, I'm moving some distance. Okay, now, it turns out that 1 radian, that I'll just put 1 theta right here, 1 radian is simply the angle that produces, and I'm just going to say makes, an arc whose length is equal to the radius. I'm going to say r. So all we got to do is a curved path that's the same length of a radius. Now, as soon as we do this, we get all sorts of stuff worked out. Once we have this value, we're not going to go into the nitty-gritty math in here, but how many radians do we need to get around the whole circle? 2 pi of them. So we're going to do this a couple different ways. I'm going to say 2 pi, or, and I'll switch color here, how many degrees? 360 degrees is a full circle. Okay, now the part about this that, again, I'm just trying to push through here, we get some really nice stuff out of here. Specifically, if we have 2 pi as a half circle, sorry, a full circle, what's 1 pi? I'm just going to say equals this time. How many degrees is 1 pi radians? 180 degrees. Now, from this, we get all sorts of information that we can use. We're going to get our real formal value or definition of a radian. A radian is very specifically defined. If S and R are the same, we're just going to say that theta in radians is equal to your arc length, which you can just write S if you'd like, divided by, what do you think? If I know, say it again, R, radius, which could be 1 if that's what somebody said. If you're thinking of the unit circle, I agree with you. Okay, alternatively, we have this equation that can be written as follows. S over R equals theta. The reason we care about this is because if I need to figure out how far along I go on any particular arc, can I solve for S pretty easily? Absolutely. We just multiply by R, and we now have a way to calculate the distance that I travel on that sort of path. Okay. Now, going through this, we are going to take this, and I'm going to box this because this is such a fundamental idea that we're going to keep seeing. This is important. This is the definition of a radian and how we're going to be able to work out the radius given an arc length and an angle, or the arc length given an angle and a radius, so forth and so on. Whatever combination we have. All right. Real quickly, I want you guys to do a short example for me. I want you to find, in this example, find me the angular displacement, or delta theta, if you will, in radians. And I'm going to write it as rads and degrees. I want both of them. For Earth, over, let's say, 36 hours of time. Cool. I'm going to pause the video. I want you guys to determine delta theta for our planet over 36 hours. Some of you are probably already done. That's okay. Talk it out. We'll give it a second. I want to make sure we're in the habit of being able to show a little bit of work with it. Cool. I'll give you a moment. If we're trying to show it, what I would do is I would say 24 hours, and there's not going to be as formal as a setup for this because it's just us thinking about it, but every 24 hours, Earth turns, and I'm just going to call it E, turns, and you guys were able to give me this a second ago because I made you all stand up and do it. Over 24 hours, how far does the Earth turn? How about just 24 hours? 360 degrees, or 2 pi radians. Now, the weird part about radians, because you're just getting it from taking the length of an arc, probably in meters, over the radius in meters, all the units fall out. There's no units on radians, which make them so much nicer because you don't have to worry about them. Okay, but for 36 hours, there's another half spin, right? So I'll just go back here and say plus 1/2 spin, which in this case would be plus 180 degrees, or plus how many radian? Pi of them, because it's a half a circle. And check it out, at this point, we now get our full rotation. Like Holloway at the X Games, over 36 hours, the Earth does what?
540.
540, that is right. I actually have some truth to drop on you. I've never been to the X Games. I did break my wrist rollerblading, though, so that killed all my ambition. What about in radians? Say that again? 3 pi. I thought I heard over 2 with it. Did I hear over 2 with it? Okay, my bad. Okay, looking at this. Doable? Okay. To convert between radians and degrees, we need a clever choice of 1 to multiply by. You may not need to have this in your notes because we have beat this to death in pre-calc, but in case we need it, radians to degrees. And I'm also going to have a thing that goes from degrees to radians. Okay, if you want to go from radians to degrees, you're going to multiply by a clever choice of 1. Now, I'm just going to say mult by, and then let's think this out again, just to make sure we still have it. Radians to degrees means I want to end up with degrees in my numerator when I'm doing this multiplication. How much is a half circle in degrees? 180 degrees. So that's a half of a turn, right? Over, is there a half circle that we could do in radians? It's pi. Okay, boom, we're done. What if, just maybe, I wanted to go from degrees to radians instead? I'll multiply by. This time I want to have my units fall out. So here's a half circle in radians. It's pi over 180 degrees. And I would see that, hey, the degree symbols would cancel out. Cool. Please reach out if you're watching this and you're looking at it going, I don't know what the hell's going on. I can talk you through it, but I don't want to talk any more about it right now if that's okay with you guys. Okay, sweet. Now, looking at it, we're going to get into the more fun stuff. Before continuing, any issues with any part of what we've done thus far? Cool. All right, here we go. We are starting our second main topic. We've talked about angular displacement. It's 2 pi theta, like whatever the angle happens to be. The first thing that we're going to deal with is what we will refer to lovingly as angular velocity. Now, we get a Greek letter. We get a lovely lowercase Greek letter for this. We are going to use a lowercase omega. It looks like a dumb W. This is omega, lowercase omega. This represents our angular velocity. Now, if I think about just velocity, like way back, regular old linear velocity, what is it? And how do you find it? I guess is probably a more clear question. It's distance that you travel over or divided by some time, right? Because we get distance in meters, time in seconds, or distance in miles, time in hours. And we get all those sorts of speeds and velocities. For this one, I don't care about the linear velocity. I don't want the speed in meters per second. I care about how what changes. Do you think? The angle. So check it out. This almost feels silly to write, but we're going to say that this is the rate. The rate at which our central angle, changes. Now, I just want to highlight here, our central angle changing, We've already defined, I looked at you and it almost happened. Our central angle changing has a name. What do we use for the change in something? Delta. And what do we use for the angle? Oh, my angular displacement is naturally just included right in this. So, right off the bat, here we go. Big important idea. We get our angular velocity, omega. Now, instead of being a change in distance, we're just going to say it's a change in angle. So we'll just simply call this delta theta over, and I'm going to be formal this time, I'm going to call it delta t. In practice, when we do this, we're pretty much always going to start with what as our time initially. So it will be in seconds normally, but the value is 0. I like both those answers. Which means when you see me do calculations, there is almost a 0% chance that you're going to see me put delta. I will 99% of the time just call it t. I'm going to write it because this is truly correct, and this is what it is, but if we start with 0, we don't need to show it. It's just minus 0. Cool. All right. Now, important little note just on the side here, entirely up to you if you want to jot down. In reality, this is really the average. This is truly average, and I use AVG, angular velocity. Now, we're just going to take a trip back to see, I'm pretty sure we talked about it in here, but I teach a lot of classes that have a lot of overlap. If I want to show you that we have velocity V, but I'm talking about the average, anybody remember the mark that we put above it? It's a bar. V bar is average velocity, which means when we look at this calculation, what we really have here isn't just omega, but it's omega bar. Now, when we're seeing this, is it possible that some things in the universe, or just whatever we're dealing with, it could be a bike pedal, doesn't matter, is it possible that the angle that it changes at, like, could it go like this and go kind of slow and then speeds up and then slow back down and then speeds back up? Like, it changes consistently, right? This does not account for it. If we wanted to get the angular velocity omega at a very specific instance in time, we would have to use some calculus, and it would just be the slope of this graph for angular velocity over time. Take the slope at any point, and you're going to get the instantaneous rate of change. That's called a derivative. That's a calc idea. We don't do calc in here, unfortunately. Cool. So let's see if we can't tie this together with another one. And what I mean by that is a small little subsection. I'm just going to keep it same color. Let's connect this idea of omega, which is our what again? Angular velocity. Let's connect that velocity with v. Now, if you want it angular velocity, and I just want to make sure that we have this, and what's this one? Velocity. Now, we need to be a little bit more clear. Instead of saying it's the velocity, because this is also velocity, we're going to be more specific. We're going to refer to this as our linear velocity. And the reason we refer to it as that is it doesn't matter if you're turning, whatever the case is. If I say, how fast are you going? And I said, quit accelerating, which means no more turning because that's centripetal acceleration. Just go in a straight line, how fast would you be going? That's what this value always gives us. Okay, we're going to compare these. So let's see if we can't knock this out. If I wanted to find velocity, just v, you guys were able to remind me a second ago, and I'll switch back to black. How do you find velocity? Okay, distance over time, I think we normally write delta x over, and I'm just going to call this delta t. I will do it formally. Are you guys okay with that? Now, if we're on a circle, and we're trying to move in a circular path, how do you get delta x along a circle? So I'm going to keep using this red thing. I'm going to make a few little notes. If we have a circle, ooh, say that again? So maybe part of it. Let's say I've gone this part of a circle. How would you figure out how far along the path I've walked? Or more specifically, the arc length. Is there a way to find it? Holy, say that again? So radius times degrees doesn't quite do it. Radius times your angle in radians will do this. Now, very specifically, I'm just going to say this displacement, the displacement that we see in this formula, if we're on a circle, it's going to be equal to r theta, or specifically part of a circle. Do you guys agree with that? Is arc length is what I'll write first. S. On a circle, the distance that we travel is the arc length, and we just denote it S. Everybody good? Which means on my next line, what can I replace delta x with? We just said it was equal to something else. So r theta, and I'm going to do this in one line. We're going to write something else first. It is the arc length S over time. Now, if you don't want to include this one, that's okay. Up above, I referenced this at the very beginning. We have theta equals S over R. That's on your page right now if you look up like 5 lines. That can be rearranged to find that S is R theta. So let's do that. Velocity then, I think, can be thought of as R theta over time. And I will make this note just showing from here to here. Theta equals S over R implies that S equals R theta. Cannot stress this enough. What is theta in? Radians. It has to be in radians. If you're in degrees, you need to do x degrees out of 360 times 2 pi r. It gives you the same thing. Radians, which shorthand is rads. Okay. Now, as we look at it, what does that theta typically represent? It's some amount of something with an angle. Every angle starts somewhere and then it turns some amount, right? That's how you make an angle. Do you agree that this theta right here then is really some delta theta? Like, we didn't write delta theta, but that's what it is, because you have to change an angle to make it. As we look at that then, I'm just going to do one little tiny rearrangement. If I wanted to, and I do, and I know how fractions work, I'm going to make that delta t again. That's my bad. Nature to not do it. Can I break up a fraction like this? I have r times theta over t, right? Could I break it up if I wanted to? What could come out in front? It could be theta times r over t, or could I write it like this as well? R times theta over t. Can I do the same thing? Now, if I want to, I'm going to be really specific with this. I should have put delta theta here before, but I want to make sure this connection is clear. I've just rearranged the fraction. Now, for this, if you are struggling, you don't see something I've done, now is like the perfect time to ask before we make our big final conclusion. Okay, I'm going to hold you honest with this. Mickey, what's this S represent, and why did we replace it here? So I'm going to give you guys about a minute for prep. I'm going to ask random people around what different parts of this mean and why we're allowed to do it. Give it a minute, talk it out. If there's something you don't understand, it's a good chance to ask me, your neighbors, a higher power, whoever it is you're going to contact. We're going to ask about it here in a second. Okay, looking at this. Why am I allowed to replace delta x with s? Yeah, it's literally the amount of distance that you have to walk around the outside of the circle, as defined with radians. Okay, there's really no other question to ask here other than that one. That was the question. Do you understand what was just said? Did you know it before? Okay. I didn't know if I just put you on the spot. Okay, bigger moment. This little rewrite seems like it may be arbitrary. Kalisha noticed right away, though, that it was not arbitrary. Kalisha, on your page, you pointed to something when I was back there. You said, hey, delta theta over delta t, we can rewrite it. What's delta theta over delta t? The amount of angle that we change in some amount of time. O. You can just call it the English letter and we'll write it. W, omega. Check it out. We can find linear velocity or angular velocity if we know the other one, as long as we have a radius. These move back and forth. As we're looking at this, I just want to make sure that we have both of them, and I'm going to start the box thing that I did above. I'm going to start making that more common so it's easier to pick out. Or, could we solve this for omega? Omega would be given in what? velocity over radius. Okay, as we go through here, I'm going to do one more little tiny comment, and this is a natural stopping point. If I were to look at omega, just omega, we have some amount of angle, whether it's degrees or radians, per second. I'm just going to say this unit is either angle per second, if it's in degrees, or it's just per second, if it's radians. You wouldn't have to say radians per second. You can just say per second, which is weird, but it works. Okay. Per second. That's a good question. I'm going to say angle per time. That's a better way to write that. Great point, Sean. Okay. Now, we can see here playing the unit game, and you don't need to do this, but velocity is typically meters per second, and radius is usually meters, right? So instead of dividing by meters, it's like me multiplying by 1 over m, and this is exactly what I just commented on. It's per second is all that you get. It's whatever unit you're with. It's either radians, and there's nothing, or it's degrees per second. Cool. We will pick up here tomorrow and find exactly how fast does one move at the equator of our planet. Later, Raiders. I was going to make you guys do poems. All right, you lucked out. Be prepared to give it on Monday. All right, later, guys.